Is it possible for object to stop in a perfectly inelastic, or in a perfectly elastic?
Yes. I mean, if I have something at rest here and then something of the same mass comes along and hits it, this should stop and that one should go.
What if they're both moving originally?
If they're both moving originally, if they had different masses, I think you could probably come up with a scenario where that works.
Would you consider duct tape to be friction? Because it keeps something from moving unless it's too heavy.
I probably would not consider it friction because I think the mechanics, the mechanisms in adhesion are different than friction. But I imagine you could come up with a decent friction approximation.
Should have wrote your thesis on that.
Oh, I actually brought it. It's in
Brought it, I wanna see it.
at the break. Remind me, I can come in and show you my thesis and my dissertation.
Oh boy. Did you get a good grade?
It's basically you get the master's or the PhD or you're done.
Do you have a PhD?
Yes,
So you had to write 2 different theses.
I did because I wasn't originally planning to go for a PhD, so I got my master's. I started on my master's and then in a class, professor said, well, I've got a PhD, I have a doctoral topic, if anyone's interested. And so I did look at my wife and I said, hey, you willing to put up with it while I go for a PhD? She said, sure. But I had already put in so much time for my master's, I went ahead and finished that.
Yeah.
All right, so there was a question about problem number 8 on the master set. So we'll do a similar problem. Doesn't really contrast with what else I do. Trouble is, I can't really change the background color. Ooh, can I do that? Yes, I can. There we go. Never mind. All right. And assume smooth transition as it goes from one surface to another. So let's make this 10 meters. And what else did I give? Oh, I gave this 15 meters. Make sure it's not exactly the same ratio. And then I had another mass down here. And I threw a spring in at the end. Apparently it changed colors for some reason. All right, so A comes down, smacks into B, and they, A and B stick. No, A and B don't stick. It is a perfectly elastic collision.
Woo! Physics!
There, okay. This time we recorded it.
Yeah.
Yeah. I assume, I think I have that money.
Yeah.
Okay. All right, so typically when you're faced with a problem like this, we've got a couple different things going on here. So we have, just call this point I, 2, then we have just before the collision, then just after the collision. And then B shoots on, and A comes back up. And just using these as labels. So A is, when A goes from its transition from the top down here to down there, there's no collision. Momentum, we could solve it with momentum, but that's not the most convenient way. Energy is actually the most convenient way. So we'll do a conservation of energy for answering part A. Because once it gets down to here, it's frictionless, so once it gets to here, how fast it's going just before it collides into B would be the same speed as at this point right here. Now, as A is moving down the ramp, what are the forces acting on it?
Gravity. Force, weight.
And,
Mole force.
all right, so I have two different forces here. One is conservative and one is non-conservative. Which one's non-conservative? And how much work does the normal force do?
0.
Right. So energy is conserved, and this does no work because it's perpendicular to the movement. So therefore, once we establish energy is conserved, well, we have the initial energy at the top is equal to the energy at the bottom. I have two types. And at this point, all of you should know this. What's the formula for kinetic energy?
1/2 mv squared.
What's the formula for potential energy?
Which one?
The one associated with weight.
mgh.
Is equal to 1/2 the same stuff but final. Now we can get rid of some stuff just to simplify the math. Is any of this equal to 0?
H of f is 0, right?
Why?
Because the 0 is, in this context, the ground.
Why?
So I'm assuming that.
Okay.
That went my nephew. Why? Why?
Because Cooper says so. All right, so we're establishing 0 to be here. H is equal to 0. Anything else we can get rid of?
Mass.
Yes. It's a common factor in every term. Anything else?
Oh, it starts at rest.
I was trying to remember with that part. Okay, if it starts at rest. Or close enough. All right, so we're left with a much simpler equation. It ultimately just comes down to g times the initial height is equal to 1/2 vf squared. Or the speed at the bottom is just the square root of 2gh initial. I assume I did not specify a planet. So we'll assume Earth. So the speed at the bottom, so V2, so we had established V1 was 0 meters per second, and V2 would be at the bottom, which would be the square root of 2 times 9.8 times, my example problem here, 10, which is 14.1 or so.
Where's that chopstick?
Which one is turning right here?
Wherever the stack is.
Gotcha.
I went to a church in Charlotte where if someone's phone would ring, in the middle of a sermon, the preacher would stop talking. It was dealt with. Because you get that moment where someone's going, like, just pretend it's not there, it won't happen, nothing's gonna happen. They just get silent,
What happened?
except for the ring. All right, so assuming my answer is right, actually, it might be 14 even. Anybody actually do it?
What question is this from?
This is similar to problem 8. I changed the numbers.
On,
The master set 8.
oh,
Seven,
turn mine in.
Yeah, it's 14.
Mine's way up there.
Okay, so 14.
Yeah, actually,
Yeah, yeah. Yeah, this could have waited. I know you're excited to hand stuff in, but, you know, you don't have to do this from the camera.
I was just trying to let you know.
Yeah. All right. So since we're dealing with a frictionless situation, we know how fast it's going at this point right here. There's nothing to slow it down as it cruises towards B. So then we get to it's going to crash into B, collision, conservation of momentum. Any questions on this before I erase it? Okay. So now we're dealing with a momentum problem. I have I guess I need to know the relative masses today. I did give them, so let's come up with some other numbers. Let's make this 4 kilograms and make this 7 kilograms. So I have a 4 kilogram mass cruising along at 14 meters per second. Gonna hit a 7 kilogram mass, which is at rest. This is before the collision. I believe it's a perfectly elastic collision. Well, I might change it if 4 doesn't bounce backward. So, I know initial momentum is equal to final momentum. I know initial kinetic energy is equal to final kinetic energy. So now it comes down to what technique do you want to use in order to do it. There's 3 techniques that we went over in class last week as well as in the videos. Well, I'm gonna take technique number 3 because that's the one I prefer, unless you have any preference.
Speed of approach.
Pardon?
The speed of approach one,
Oh,
to do that one.
method 2? Okay. So we're doing method 2. My total momentum here is 4 times 14, which is 56. So 56 plus 0 is equal to, I'll just call it 4A plus 7B, where these are the final speeds. And then we have relative speed of approach equals relative speed of recession. In other words, 14 minus 0 is going to be equal to B minus A. So the difference in the velocities initial is equal to the difference in the velocities final, just flipping the order. So from this equation right here, I know that B is equal to A plus 14. Pop that into the first one, I got 56 is equal to 4A plus 7A plus 14. Distribute. 56 is equal to 4A plus 7A plus 98. So 11A is equal to negative 42. A is equal to negative 42/11 meters per second. B is going to be equal to 14 plus that, whatever that is. So 14, so this is negative 42/11 plus 154/11. 11th. 10 point. See, 2/11 is. That 1/8, 1/8, 1/8, 1/8, no.
Are you talking about the A?
So what is A?
Negative 3.81 for PM.
8-1 repeats or just the one?
8.1.
So this would be, oh, it is 20 repeats. Here. Is it? Okay. Meters per second. So we now know how fast they're going after the collision, and then it basically breaks into two different bits. How far up the ramp does A go, and what's the maximum compression of the spring? Questions up to here. All right, so A has lost energy, transferred it over to B. We have how fast it is going. The negative indicates that it is getting back opposite the way it was going right before the collision, because when I established that as 56, I established that that was the positive direction, which I should have written down before I started the problem. A is cruising back this way, going up the ramp. It's again, it's a conservation of energy problem. We are left with the exact same situation as we were before, except final becomes initial. So we basically end up with GH final is equal to 1/2 V initial squared. Going through the exact same process we did before, just reversing it. So H final is equal to 1/2 V naught squared over G. So that's 1/2 times 3.81 repeating squared over 9.8. And this gets us an answer, not the answer to the question, but an answer. .744. 744. Okay. Units?
Meters.
Yeah. Now the question is asking how far up the ramp does it go? How far up the ramp does it go? What we just found was this distance right here. There are a couple of ways to approach this, but we do have some more triangles here. We have the big triangle, where that's 15 and that's 10. And then we have this smaller triangle, where this is 0.744, and that's what we're trying to figure out. And so 0.744 is to 10, as x is to 15, or there are other ways of setting that up. Or if you like the trick, you could find the angle and use trig that way. And so x ends up being 1.5 times this. Roughly is 372, so 6, 1, 1.116. Yeah. Okay. So that's how far up the ramp it goes. Not very far. Questions there?
Could you explain the equations in red again?
These?
Yeah.
It's a conservation of energy problem as it goes back up. Now, we had the stuff that was written over here that would have been nice if we still had up there. But in essence, we have still energy is conserved, because this is post-collision. K initial plus K plus U initial equals K final plus U final. Initially, well, 1/2 mv squared plus initial plus mgh initial equals 1/2 mv final squared plus mgh final. It's the same setup as we had before. Let's keep h is equal to 0 where we had it before, so that's 0, again, because Cooper said so. That's 0 because it's going to stop. And what we're left with is 1/2 times the initial speed squared is equal to GH final.
Okay, that
That's
makes sense.
where it comes from. Other questions? All right, so now we're dealing with B crashing into the spring. Is that an energy or a momentum issue?
Momentum,
Why?
because they're colliding.
What's the mass of the spring?
It's massless, according to the problem.
So if it's massless, makes it very difficult to do momentum.
Okay, energy.
Ah, yes. Sorry. Puberty, my voice is changing. It is, and before I did talk about there's a collision, therefore momentum. This is sort of an exception to that because the ideal spring, which it is, exerts a conservative force. So energy is conserved. So we're left with this 7 kilogram mass traveling at 10.18 repeating meters per second. I know K initial plus U initial equals K final plus U final. Because the forces acting on this, right now, the forces, we have weight acting down and normal force acting up. Neither are doing any work, so the kinetic energy is staying the same.